Hello and welcome once again to Mathspirational. This is the second video in my series on gradients of curves, and in it we are going to estimate the gradient of a curve at a particular point. The curve we're going to look at is y equals x squared, and our point A has coordinates 1.2, 1.44. Now those of you who did use of maths will have gone through and estimated gradients at points in your algebra module by drawing on a tangent at the point and then working out the gradient of that tangent. And you'll have discovered that it's time consuming and significantly error prone. It's actually very difficult to draw an accurate tangent onto a graph. However, in order to be able to find the gradient at a point of the curve, we need the gradient of that tangent. So what we're going to look at today is estimating the gradient of that tangent by first looking at the gradient of a chord of a line segment. To show you what I mean, I'll bring up GeoGebra. So here I have exactly the same curve, y equals x squared, point A, which is still 1.2, 1.44, and on it I have attached the tangent, of which the gradient is 2.4, and GeoGebra quite nicely tells us that. However, in reality, we're not going to have GeoGebra to hand most of the time in order to quite nicely work out the gradient, so we need another way of doing it. I mentioned line segments. What do I mean by that? I mean that if I take another point on the curve, B, and join it to A via a line segment, I create a chord on that line between A and B. Now we can see that the gradient of our line segment AB, or our chord AB, isn't the same as the gradient of our tangent. Clearly isn't. However, we can also see that if we take B and move it closer to A, then the gradient of that blue line gets closer to the gradient of the tangent. And I can show that to you somewhat better because down here I've got the gradient of the line segment. So I've got a gradient of a line segment is equal to delta y over delta x, where delta y is the change in vertical distance between A and B, and delta x is the change in horizontal distance between A and B. And at the moment, that's 3.22. I've used lowercase delta, and really at this stage I should have been using the capital delta because they're quite large numbers. However, you can see that as I slide B down towards A, the value of delta y over delta x rapidly approaches that of the gradient of the tangent. As we get really close to it, when delta actually becomes a lowercase delta, and we have 0.14 over 0.06, we've got a gradient of 2.46, which is pretty close to 2.4. As we move it even closer, that delta y over delta x is even closer to the actual value of our gradient. So what we need to do then is find a way of doing that numerically without having to draw the graphs and put on the tangents and the chords, which we're going to look at now. We're trying to find then the gradient of our black chord here. And as I said, we're going to do that by finding the gradient of a chord joining up 2 points A and B, where B is close to A. So in this case, we're going to have to find the gradient of our line segment. So for that, we're going to have to find what delta y and delta x are. So at point A, x is 1.2 and y is 1.44. Now we've said that delta x and delta y are small changes in x and y. So let's say we go across just 0.01, so that b will be at 1.21, and so its y coordinate will be 1.4641. So it gives us gradient of our chord, delta y over delta x, it's going to be 1.4641, take away 1.44, divided by 1.21, take away 1.2, which comes out to be 2.41. Well, that's really very close, isn't it? We saw a moment ago that the gradient was actually 2.4. So 2.41 is pretty close. But I reckon we can get closer without a significant amount of extra work. So let's scrub b being there, and instead say that b is even closer to a. Let's say it's at 1.201, which means y is going to be at 1.442 401. So delta y over delta x is now going to be 1.442401, take away 1.44, over 1.201, take away 1.2, which gives us 2.401. Wow, that's even closer. That's really very close to 2.4. But again, we can go even closer by saying b is actually going to be at 1.2001. Now, I'll save you going through the delta y's and the delta x's. If we do that, then delta y over delta x becomes 2.4001. And similarly, no prizes for spotting that if I chose b to be at 1.20001, then delta y over delta x is going to be at 2.40001. The closer b comes to a, the closer delta y over delta x comes to being the actual gradient. So, if you're in a position in an exam where you're asked to numerically estimate the gradient at a point, take a point A, find its x and y coordinates, take a point very close to it. You'll either be given a point close to it, or you have an equation in order to be able to find out the y coordinate of an x coordinate that's very close to it. And then, just as in a straight line graph question, you find the gradient by doing change in y, delta y now, because it's a very small change, divided by a change in x, delta x. In my next video, we're going to start looking at how to create an equation that will give us the gradient at any point on a function. And for that, I'm going to start again with y equals x squared. Thank you very much for listening. Hope that was helpful. If you liked it, please like and subscribe.